wasn't that bad. You can fly an unstable airplane if you've got a good horizon reference. You know, where people lose control of an unstable airplane is trying to fly it on a 3-inch instrument. Okay, you can't have that. In fact, another one of the things we learned out at the SETP was that the SR-71, initially they flew it in the day VFR. And at night, pilots were losing control of it because they didn't have a good horizon reference. So they put their own horizon reference with a laser line across the cockpit. You know, we don't realize, but we use our peripheral vision in flying an airplane very much. And when you take away your peripheral vision and roll it into a 3-inch instrument, all of a sudden your workload just goes out of sight. Most of you, or those of you who've worked on an instrument rating, tend to realize how, you know, what happens when you take away those, you know, we sell our bodies short in engineering, I think. You know, we tend to, and this is the thing about all this automatic stuff that's going on now. Human computer's damn good, okay, and the human eye is probably even better. We can sense a 1/4 degree change in attitude if we have a good horizon reference. Well, when you shrink that nice natural horizon into that 3-inch instrument, you're lucky if you can figure out 5 degrees change. So that's, you know, that's a part of it. And this was the thing with the jetwing. It wasn't that difficult to fly VFR. I never tried it IFR, okay? Number one, it only had about a 45-minute legs. So generally I wanted to have it back on the ground in 45 minutes. But anyway, you know, we had a whole series of these plots because we did it for a whole bunch of different airspeeds and configurations, thrust configurations. Well, and in this case, lift is equal to the weight times the cosine of the flight path angle. Now, you know, in normal conditions, we say sine and cosine are close together, so we ignore it. In a powered lift airplane, you can't, so it's lift equal to weight times the cosine rather than the sine, okay? For small angles, sine is fine, and we generally use it that way, but you can't really do it here. And when we write that in you know, coefficient form, we can come up with a plot of CL, or a plot of that versus CL. And well, we need some method to correct that data to a single sea level standard day conditions. A fellow by the name of Parks, he was a professor out at Arizona State, developed this method. He was out at Edwards during the YC-14, YC-15 program, and for a summer, as a summer faculty kind of thing. And he was asked to develop this, or come up with a method that would work for the flight test of those airplanes. And so what he did, he came up with that for a given configuration, the value of the tangent of the flight path angle for steady state conditions won't vary if both CL and blowing coefficient, and blowing coefficient in the case of the jetwing airplane was just gross thrust over dynamic pressure times the wing area, thrust over QS. If I held those constant, well, then you could come up with the equation. Now here's the equation. Here's the performance equation for a powered lift airplane. Excess thrust coefficient, CFEX. Okay, that's, you know, that's this area here, excess thrust coefficient. is equal to, in this case for like the jet wing where you're blowing everything over, CJ, thrust over QS, minus KCL squared over pi aspect ratio. That's the lift term in a normal, for a normal airplane, but notice what happens here. You got 2 times the blowing coefficient in the denominator. What does that do to the induced drag? If we can call it induced drag. All of a sudden, see, drag and lift and thrust all get mixed up. But what's going on here in this area is because of that. And sure enough, the wind tunnel showed that, showed the flight test, showed that. And I think we've missed a terrible opportunity here to come up with airplanes that would do some very strange things. As a matter of fact, that's how I got my doctorate, was on this sort of thing. On power lift airplanes, how, to do both performance and stability control and how to predict it. But anyway, so this is the new equation that you work with, where this excess thrust coefficient, is defined. Like I say, with a conventional airplane, it's, yeah, you'll have excess thrust. You'll have an excess thrust coefficient if you want to take it that way. But it's not, the shape of the curve is not going to vary significantly from your drag curve. Until you start blowing air over the wing. And then, here's what happens. Now, Parks used this equation. He did not develop this equation, but he used it. It was developed in England by a fellow by the name of Williams and some other folks. Yes, sir.
I'm a little confused with CJ. That CJ
Yes.
comes from thrust, right?
Yes.
So we're missing the Oswald coefficient in there.
Where's what?
E. So we're missing the E. Is that E going to be embedded on that term?
It's in that
Okay.
term. Okay. It's, it's embedded in the K in this equation.
This was proven experimental and theoretical.
Yeah, now Williams, who developed the equation originally, did it on a powered lift airplane that they had in Britain, and it was done in a tunnel. YC-14 and YC-15, YC-15 when the flaps are down, and now C-17 when the flaps are down, obey this equation. YC-14, of course, blew all the air, both engines over the upper surface. And the NASA Quiet Short Haul Research Aircraft, QSRA, which was a de Havilland Buffalo with 4 engines mounted on the wing. They were doing their stuff at about the same time I was doing the jet wing airplane in the 80s. And we made a lot of comparisons back and forth. But folks don't understand this. They don't understand this additional term, what it does for you. And let me tell you how I learned it in the real world. This was a single place airplane. There wasn't any checkout. You You strapped it to your behind and went out and flew it. And I'm on my first flight in, see, and I take off, and that's pretty much normal. Went out and flew it around for a while and kind of got the feel of it. Came back in, and I said, let's see, powered lift airplane. I'm not sure I want to use full flaps, so I'll only put down about 20 degrees of flaps rather than 30 or 45. And powered lift airplane, so I'm not sure I want to pull the power all the way to idle or pull it back too far. Because, powered lift may become an instant rock. So, so I fly, here's the airport, and I fly around the airport, and I come back in, and I'm still not wanting to pull the power back very much, and I come over the airport. And now, in a conventional airplane that isn't powered lift, if you're on the backside of the power curve, so to speak, if you just dump the nose to increase the airspeed, you'll come down. Not so in a powered lift airplane. I come around and I, turn on final, and I don't want to pull the power back. So I said, well, backside of the curve, I'll just put the nose down. So I put the nose down and watched the airport go by. Said, this isn't working. So I learned that I really had to adjust the power, and I'll show you why in a minute.
So that's the connection between lift generation and thrust.
Yeah, this was flight path angle. Throttle was flight path angle.
And that CG reflects that.
Yes, oh, very much so, because all of a sudden the induced drag wasn't what it was, because we're blowing air over the wing and the flaps. The induced drag had decreased due to two times,
This square.
Yeah. See, the rest of that thing, other than the fact that, you've got E in this term, if you take this away, that's just the induced drag term, right? So if you take that away, it's just conventional airplane. But when you start blowing, this appears in the denominator, and you, all of a sudden, like I say, this airplane flew as much like a helicopter as it did an airplane. Now, in a helicopter, this is definitely flight path control, okay? And this is pretty much airspeed. That's just kind of backwards in a conventional airplane. But this powered lift airplane was very much, like a helicopter. And the first, when you added power, we did the airspeed calibration by using a pace, because I didn't want to do, at that time, I didn't have GPS, okay? So I didn't want to use a speed course where you fly, close to the ground with a powered lift airplane. If the engine quits, you got about 2 seconds to think I'm going to die. Not a good plan. So we took it to altitude, and we actually, to do the airspeed calibration, we used a de Havilland Otter, which will fly a level at about 35 knots. We used that for the low speed, and a Cessna 310 that we had for the high speed part of the airspeed cal. But we had both of those airplanes with airspeed cals, and we were able to get this one. But what I started to tell you was, when we were flying pace on this airplane, if you added power, first you went up, and then you had to, it was a combination thing. When you added thrust, you had to increase airspeed with the stick. So it was a strange airplane.
So the speed range was literally 35 to 150 to 100?
Pretty much. I'll show you some of the performance curves here in a minute. Anyway, that's the equation for a powered lift airplane. Well, to do the flight test, these equations look like you've seen before. Here's what we call VIW, in this case I call it VEW for equivalent, okay, but where we have equivalent, you know, square root of the weight ratio, VIW, same animal. Here's for thrust, again you set, here's the standard gross thrust, here's the gross thrust you measured, essentially the test condition. Flight path angle is the same, but this is test weight and standard weight, and so then the standard gross thrust is just equal to the measured gross thrust divided by the weight ratio. So those are the equations that apply to the method. You can collect the data by making climbs and descents at constant airspeeds and power settings, which is what we did. And you use several power settings at each airspeed. So you can see this was a rather large flight test to get this performance data for this airplane. Fortunately, the US Navy was paying for it, and because the Navy was interested at the time. See, in the early 80s, when Jimmy Carter was president, the Navy was talking about doing away with large deck aircraft carriers. And so they were looking for various technologies, either VTOL, STOL, or what have you. This was an STOL technology that the Navy was interested in. And so they gave me a research contract to look at this airplane and do the performance on it. Turned out that the Ball Corporation donated the airplane and its conceptual patents to the University of Tennessee, and that's how I came by the airplane. But anyway, this is a collect the data, climbs and descents, constant power settings, with several power settings for each airplane. Plot the pressure, altitude versus time, just like we did for their climbing thing. Take the slope of that altitude versus time graph, just like we did, okay? And then we plot the data for each airspeed, and the combined maps of flight path angle versus airspeed can be constructed from the gross thrust versus airspeed plot. Here's the data reduction technique, pretty much like we've done. And here's one of the plots first plots you developed. This is gross thrust, standard gross thrust versus flight path angle. And these are straight lines. Now, one of my students, this was a power off, idle thrust. And although sometimes it fell off of a straight line curve, almost all these curves are straight line. And one of my students came to me one day with this same plot that went like this, because this point was up here someplace. And he handed that to me and he said, well, he says, this doesn't look right. And I said, well, obviously that bottom point was wrong. And he said, well, it came out of the computer. I said, yeah, garbage in, garbage out. And sure enough, he had taken the wrong thrust level for that particular point when he entered it into the data reduction scheme. But I laughed about that all the time. This is this particular point is N1, engine fan speed over root theta, which is how you normalize that data. And it's at 75% or 79% N1 over root theta. And then with all of those plots, there's a whole bunch of those plots that I just showed you. Here's the map. Here's the performance map. This is with 15 flaps, okay? Notice that with 15 flaps, that your thrust level here is about 1,000 pounds of thrust. Still got some climb capability here at just 1,000 pounds of thrust. Look at if you go full power. You know, I just stopped it at this point, but if you carried that on over, where would that go? This thing would have, if you cured the tail stall, it would have flown level flight at about 35 knots. Okay, weighed 3,700 pounds, had 105 square feet of wing area. Now Cessna 150 has 175 square feet of wing area. Yes, it will fly slower than the Cessna 150. And yeah, the 150 won't go up with the flaps down.
With the flaps down.
You know, but notice how flat these curves are. See, that was what the trouble I got into on that first approach. Was that, you know, here I've got some flap down and I'm making a, you know, about a 3-degree descent, and this curve is so flat that, you know, and I increased airspeed and nothing happened. Flight path angle didn't change. If this was a conventional airplane, these curves would look like this. So that's the advantage of powered lift. I think I've got another, oh, I guess that's it. But it would go, this airplane would go about 180 knots in level flight, indicated. I could enter the field at Tullahoma, Tennessee was a mile in diameter. I could enter the airport enter the field at 180 knots, crank it into a turn, and stay within the confines of the field. If you really took advantage of this kind of thing, you have to do something with the pilot. Because with this kind of an airplane, you can pull a sustaining 9 Gs. You know, I mean, most of today's airplane will pull 9 or 10 Gs, but not sustain. And again, like I say, that's where you end up in here. But we've missed that point.
What happened